Hey guys, this week we are going to talk about 2.6, 3.1, and 3.2 in the textbook. First thing we're going to talk about is differentiability. So what does it mean for a function to be differentiable at a point? Then we're going to talk about the relationship between differentiability and continuity. In 3.1, we're going to talk about a shortcut to taking the derivative, also known as the power rule. And in 3.2, we're going to look at two special types of derivatives. In particular, we're going to look at the derivative of e to the x, and we're going to look at the derivative of exponential functions. So let's go ahead and get started with 2.6. So what does it mean for a function to be differentiable? All that means is that at every x value, the function has a derivative. In other words, the limit as h goes to 0 of f of x plus h minus f of x all over h exists. So the derivative exists. And so we're going to talk about three cases where the derivative fails to exist. But let's first look at an example of a function that is differentiable for every x. And that's going to be this function right here, this red curve. And so we can see that for every x, the slope of the tangent line to that x is going to exist, right? Sometimes it's going to be 0, sometimes it's going to be negative, sometimes it's going to be positive, but we see that it's going to exist everywhere, no problem. Now, we would have a problem if there was a point on the curve where we would have a slope that's undefined, right? So when the slope is undefined, our tangent line is going to be vertical, and we can see that in this picture we don't have that. But let's go ahead and take a look at what it means to not be able to take the derivative of a function at a certain point. So there's three different cases, as I said. The first case is that there is a corner at your x, where you're trying to differentiate. So for example, if we look at this guy right here, now this is x equals a, all right? So at the value x equals a, the derivative doesn't exist because there's a corner here. And why is that? Well, from the left-hand side, the slope of the tangent line seems to be positive. But on the right-hand side, the slope is approaching something that appears to be a negative slope. And so that is why it is not differentiable at a corner. Okay, let's look at our next case. Our next case is when we have a discontinuity. In particular, if we have a jump discontinuity like we see here, the slope of the tangent line at x equals a is going to approach something different because our function values are different at x equals a. And so that is an example of a non-differentiable point on the curve. And the third case is if we have a vertical tangent, as I mentioned on the previous slide. So when x equals a here, if I were to draw a tangent line to that point a, I would see that the tangent line is vertical, and so the slope is undefined. All right, so those are the three cases. And we have them again right here. So here's our first example. We're going to investigate the differentiability of the absolute value function at x equals 0. So the absolute value function, first of all, I graphed it right here. I used Desmos to get a graph of that. And it can be defined in the following way as a piecewise function. So the absolute value of x is going to equal x if x is bigger than or equal to 0, but it's going to equal negative x if x is less than 0. Okay, so that's a way we can define the absolute value function. So we need to figure out whether this thing is differentiable at x equals 0. And to do that, I'm going to use my limit definition of the derivative and see what happens. So we have limit definition x plus h minus f of x all divided by h. And since I'm looking at what happens when x equals 0, I'm going to plug in 0 for x. Now on your homework, I believe you're looking at what happens when x equals 1. So in that case, you would plug in 1 for x. All right, but here we're plugging in 0 for x because that's we're trying to see if it's differentiable at that point. All right, so we have f of 0 plus h is simply h minus f of 0 all over h. Well, what is f of 0? So when x is bigger than or equal to 0, f of x is x, right? And so f of 0 is simply going to be 0. All right, so we have the limit. And again, this is coming from the fact that we're using x because, you know, we're using x as our output because our input says that if x equals 0, then the function is equal to whatever we put in it. So in this case, that's 0. All right. So this is going to be the limit as h goes to 0 of f of h minus 0. That's just f of h all over h. And so we need to consider two different cases, right? Because f of h could be different depending on whether it's, x is bigger than, h is bigger than or equal to 0 or less than 0. So we need to take both cases into account. So case one, when h is bigger than or equal to 0, right? That's our input here. So it's acting like our x. It's like x is greater than or equal to 0. So that's case 1. Well, in case 1, f of h, this whole thing, is just going to be equal to h. So we have h over h, limit as h goes to 0, and that's just going to equal 1. So that's case 1. Now case 2 is going to be if h is strictly less than 0. That's the other part of the domain that I need to be concerned with, right? So if that's the case, then what do we have? F of h is going to equal negative h, right? So this is going to give us, if I plug in negative h in for f of h, I have the following. I end up getting negative 1. Okay, so the limit does not exist of the derivative because we have approached two different numbers, right, from two different sides of 0. We looked at it to the right of 0, which was case 1. We got a derivative of 1. And from the left of 0, we got negative 1. And we can kind of see that on the picture, right? Because for h is less than 0, that's going to correspond to our slope of being negative 1. And we can see that this portion of the graph has a slope of negative 1 as it goes closer, as h gets closer and closer to 0. On the other hand, for case 1, when I'm on the right side of 0, the derivative is approaching 1, right? That's the slope of this red part of the absolute value function. And so since the slopes are different, the limit does not exist. The derivative is not approaching a single value as it gets closer and closer to 0. And so we have just proved using the limit definition that f of x, we've just proved that f of x equals absolute value of x is not differentiable at x equals 0. Okay, so we just proved that. Now we're going to investigate the differentiability of f of x equals x to the 1/3 at x equals 0. Well, we have a graph right here of f of x, and we can kind of see from the graph when x equals 0, this tangent line appears to be vertical. So that's already telling us from the picture that this derivative is not going to exist. So at x equals 0. So let's go ahead and use our limit definition again. All right, so again, I'm plugging in 0 for x in this case. All right, so when I do that, I get the following. I get f of h minus f of 0 all over h. Okay. Okay, so f of h is just going to be h to the 1/3 minus f of 0. Well, if I plug in 0 in for x, I just get 0. So this is just minus 0 is 0 over h. And then I can simplify this by using my properties of exponents. So 1/3 minus 3/3 is going to give me h to the negative 2/3, which is the same thing as 1 over h to the 2/3. And you should try this out, from the left and the right side. As h gets closer and closer to 0, what's going to happen is this thing is going to blow up. It's going to get very, very large, okay? And so because of that, the limit does not exist at x equals 0 for the derivative, and we just showed that using the limit definition. And you can further prove this to yourself by seeing what happens as h gets closer and closer to 0. We'll see that this thing is going to get bigger and bigger. So there's no uniform number that the slope is approaching here. All right, so there's a theorem from your book. It says if a function is differentiable at a point, then that function is continuous at the point, okay? So if it's differentiable, it's continuous, but not the other way around. So the converse is not always true. And what's the converse? If the function is continuous, then it's differentiable. That is not always true, and we're going to see that in this next exercise. So it says, at point C, decide whether these graphs are continuous, differentiable, both, or neither. All right, well, let's look at this first one that we have here. Here is x equals c at this point right here, and it's a corner. So remember, corners are not differentiable, so we know it's not differentiable. However, it is continuous because there's no open circle, there's no jumps, there's no asymptotes. It's continuous but not differentiable. So the answer here is just A. Continuous but not differentiable. Let's look at the second one. So at x equals c, it appears that this thing is not continuous because of the open circle, and it's also not differentiable because of this, this corner, right? This thing converging on the open circle here. So this is going to be neither, which is choice D, neither differentiable nor continuous there. All right, what about this one? So at C, it appears that there's an asymptote. All right, so we know it's not continuous there. And it's not differentiable there because the curve, it gets arbitrarily close to it, but it's never going to cross it. And so again, this is going to be D. It's neither differentiable nor continuous at C. All right, let's look at this guy. So here is x equals c on the curve right here. And so it appears that our function is continuous. There's no open circle or jumps or anything like that. And it also appears to be differentiable because if I erase that, notice that right here, there's no corner or anything like that to suggest that it's not differentiable. And so this is going to be both continuous and differentiable. So that's going to be C. And let's look at this last one. So this is not going to be continuous at C because, there's an open circle right there at C. So it's not going to be continuous, and it's not going to be differentiable either because, again, just like the absolute value function, the slopes are approaching different values. The slope on the right side of c seems to be positive. The slope on the left side seems to be negative. So this is neither differentiable nor continuous. Okay. So that was the lecture. I hope you guys enjoyed and learned something. I'll see you guys next time. Thanks for watching. Hey guys, welcome to the next part in this week's lecture. This section is going to be Chapter 3, Section 1 from the textbook. And basically what we're going to be doing is talk about a shortcut to taking derivatives so we don't have to use the limit definition every time because it's pretty tedious. So just as a reminder, the derivative that we know so far as defined with limits is the following. So if we have a function f of x and we're looking at the derivative at x, aka the slope of the tangent line to x, it's defined as the limit as h goes to 0 of f of x plus h minus f of x over h. So let's get to the shortcut. So before we get to the shortcut, we need a couple of theorems. And so the first theorem is the derivative of, we're titling it the derivative of a constant multiple. And so if f is differentiable and c is a constant, then the derivative of c times f of x is just c times the derivative of f of x. Okay, so, and we're going to do a bunch of examples with this, so it is a little abstract right now, but just keep in mind that we're going to do plenty of examples. And by the way, this just means the derivative with respect to x. Okay, so just keep that in mind. Okay, our next theorem is the derivative of sum and differences. So if we have two functions, f and g, and they're differentiable, then the derivative of the sum of f plus g is equal to the derivative of f plus the derivative of g. And we have a similar story for the derivative of the difference of functions. Okay, so here's where the fun comes in. Okay, so this is called the power rule. It's super useful, like probably the most useful thing we're going to use this semester. Now, if you're curious about how this is proved, I'm not going to do the proof here just for, practicality, but the proof is in the textbook in this section if you are curious of why this is true. So basically this is telling us if we have a real number n in our exponent, then the derivative of x to the n, we just multiply n with the coefficient in front of x, and then we subtract 1 from the exponent, okay, giving us this. And so let's just do some examples to see how this works. All right, so the first one is find the derivative of y equals x to the 20th. So what we're going to do is, this is our n, right? So we multiply it by the front constant, which is just 1. So we have 20 times 1 is 20. And then what we're going to do is we're going to subtract 1 from the exponent. So this guy is y prime. This is the derivative. See how easy that is? I know you guys are going to be mad at me because I remember being mad at my calculus professor. Like, why didn't you teach me this before? Well, there's a reason. But anyway, super easy shortcut. We're going to do a bunch of examples. Let's get into it. Let's go to the next one. Okay, if f of x equals 2x to the 5th, find f prime of x. So again, n is 5. We're multiplying 5 times 2 to give us 10 in the front, keeping that x, and then 5 minus 1 is going to give us 4. Okay, so that's our derivative, f prime of x. It's as simple as that. Now, if you didn't believe me, that this is the shortcut. You could always use the limit definition to verify that this is, in fact, legit, right? All right, and so the way that we would set this up, I'm not going to evaluate it, but if you don't believe me, you should. F of x plus h, we have 2 times x plus h to the 5th minus 2x to the 5th all over h. Okay, and that's, going to take a while because it's to the 5th, but that's how you do it. And at the end, you should get 10x to the 4th as your derivative. Whoops. Okay. All right, so as I said, we're just going to do a bunch of examples in this video. So we want to find the derivative of this function 3x to the 4th minus 2x to the 3rd plus 8x minus 3. So we're going to use a combination of the first theorem we looked at, the constant times the function theorem, as well as the sum and difference of derivatives to do this, and the power rule. So we're using all three technically. And so we just differentiate term by term, right? That's how we're going to do that. Now, the derivative of a constant number is always 0, right? And, why is that? Well, if we were to stick a variable on it, if we were to stick an x on it, it would be x to the 0. And using the power rule, multiplying that by 0 is going to give us a net result of 0, right? So the derivative of any constant number is 0. Important thing to note. All right, so let's go term by term. First, 3x to the 4th. Again, using the power rule, multiply this guy. 3 times 4 is 12 in the front. X to the 4 minus 1 is 3. Okay, here we go again. 2 times negative 3 is going to give me negative 6 in the front. X to the 3 minus 1 is 2. Here we go over here. We have understood exponent of 1. 1 times 8 is positive 8 in the front. 1 minus 1 is going to be 0, right? So this is x to the 0, but we don't need to write that. It's just going to be 8. Okay, so this is y prime, and we already said that the derivative of negative 3 is just 0, so we don't even have to write that. All right, so let's do some more examples. I encourage you to pause the video and try this one on your own, see if we get the same thing. All right, so again, we're going term by term when we differentiate this guy. Now this thing's going to 0, get rid of it. Negative 5 times 10 is going to give me a negative 50 in front. Negative 5 minus 1 is negative 6. Okay, plus 2 times 4 is going to give me a positive 8 in the front. 4 minus 1 is 3. Let's see, 1 times negative 2 is going to give me a negative 2 in front. X to the 1 minus 1 is 0, but we don't have to write x as 0 because that's just 1. So this is our derivative right here. This is g prime of x. Okay, let's go down here. All right, this time our variable's t, that's okay. Again, we're going term by term. So this is understood to be 1 in front. 1 times 4/3 is 4/3. T to the 4/3 minus 1. Well, 1's the same thing as 3/3, right? And so 4/3 minus 1 is just 1/3. Plus, again, 1 times 9 is going to give me 9, t to the 0, but I don't have to write the t to the 0, so it's just plus 9. And this is going to be f prime of t. That's my derivative. All right. Now, sometimes you're going to have to use your algebra skills to manipulate these equations/expressions to take the derivative. So remember, if we have something in the denominator with a positive exponent, we can move it to the numerator and make the exponent negative. So this is secretly y equals x to the negative 4. All right. Now we take the derivative. Y prime is going to be Negative 4 times 1 is negative 4. X to the negative 4 minus 1 is negative 5. So that is my derivative there. Ba-bam. Now with square roots, we can make this into an exponent. Remember, if I have, let's see how I want to write this. If I have n as my index and my radical and x, what this is saying, where x, where n is a whole number, this is the same thing as x to the 1 over n. Okay, so that's a, fact that you probably learned a while ago in Algebra 1 or Algebra 2. So, with all of that being said, I'm going to rewrite this thing as 3 times x to the, well, when we don't have a number in the index, it's understood to be 2. So this is x to the 1 over 2 by this formula right here. All right. Okay, so now I take the derivative. So f prime of x, maybe I'll do it in purple. So f prime of x I multiply 3 times a half, which is going to give me 3 halves in front, times x to the 1 half minus 1 is the same thing as 1 half minus 2 over 2. That's going to give us negative 1 half. So that is my derivative. And you guys might be thinking this is so easy, this can't be real. It's real. Some parts of calculus, it sort of oscillates in difficulty, right? Limits are kind of hard. Honestly, they are pretty, it's a pretty difficult concept to understand. The limit definition of a derivative is also kind of hairy and not great. But then we get to this stuff and you're like, is this really calculus? Yes, it's really calculus. And there will be more ups and downs. It just so happens that calculus sort of starts on an up on the difficulty level, sort of towards the end. But yeah, hopefully it's getting easier. And anywho, let's go ahead and do number 6. Now this index is 3, meaning that this whole thing, I can rewrite this as y to the 1 over x to the 8 to the 1/3, again by this in my little cloud up here. All right. Okay. So then what I can do is I can bring that exponent to the top so that it's negative. And this is still to the 1/3. And then, use this fact from algebra that this turns into x to the negative 8/3 when I multiply it out. So y is equal to x to the negative 8/3. What we're going to do is use our power rule. So y prime is going to be negative 8/3 times 1 is negative 8/3 in front. X to the negative 8/3 minus 1 is negative 8/3 minus 3/3, which is negative 11/3. And you can simplify this if you want. I don't really care. There it is. Wiley will take, either answer if you put x back in the denominator. Okay, moving on. More examples. Here we go. Number 13. Okay, so find the derivative. Well, the first thing I'm going to do is I'm going to recognize that I am multiplying this x to the 3/4 throughout everything. Basically what I want is I don't want anything to be multiplied or divided because, we're going to learn a theorem for that later, but we want everything to be in polynomial form, right? We want it to look like this. We want it to look like, let's see, how about a to the n, x to the n, plus a to the n minus 1, x to the n minus 1 plus dot, plus a to the 0. So this is polynomial form. A sub n minus 1. Those are all coefficients. We want this thing to look like a polynomial, okay, at the end of the day. So I'm going to distribute this guy in there to do just that. And so the first one, we end up getting 2 times x to the 3/4. And then we have, well, this thing is x to the 1 over 4, right? So then we have minus x to the 1 over 4 times x to the 3 over 4. Okay? So we can simplify this more by using our exponent laws. We keep the base and we add the exponents, right? So this is going to give us, this is going to give us 2 x to the 3/4 minus x to the 1/4 plus 3/4 is 4/4, which is 1. Okay. All right, and now we do the derivative. So the derivative, and this is kind of an expression, not really a function. So when I multiply this guy, I get 3/2 in the front. 3/4 minus 1. 3/4 minus 4/4 is minus 1/4. And then the derivative of minus 1x is just minus 1. Okay, that's my derivative. All right, and let's look at number 8. We can simplify this because, again, we don't really want a quotient. We don't want a rational function. We want a polynomial. And so we can simplify this because we have x to the 3rd over x plus 2x over x. And these can be simplified. Oops, sorry about that, guys. So these can be simplified. The first one is x squared. The second one is just 2. And now we take the derivative. So the derivative of that is just 2x. The derivative of a constant, remember, is just 0. So here's our derivative. Let's see how we're doing on time. I think I'm going to keep going. All right. I think there's a question or two on your homework about finding the second derivative. So just like we did with the limit function, we're just taking the derivative twice, okay? So the first derivative, let's call both of these f of x, actually. Let's call this one f of x. Let's call this one f of x. All right, so the first derivative, f prime of x, is going to be 6x plus 4 plus 0, which we don't have to write. And then the second derivative, we're just taking the derivative of the first derivative. So derivative of 6x is just 6 using the power rule. Derivative of a constant is 0, so our second derivative is just 6. Okay, let's look at number 2. Our first derivative, f prime of x, is going to be 4/3 x to the 4/3 minus 3/3 is 1/3. All right, so that's my first derivative. My second derivative, f double prime of x, I'm just multiplying 1/3 by 4/3, which is 4/9. So this becomes 4/9 x to the 1/3 minus 1 is the same thing as 1/3 minus 3/3, which is negative 2/3. Okay, so there's my second derivative. All right, suppose g of x equals 2x to the 3rd minus 4x squared plus 2x minus 1. For which values of x is the derivative equal to 0? And then it says confirm this by graphing using Desmos. Okay, so the first thing we need to do is figure out what g prime of x is and then set equal to 0 and solve for x. All right, because it's asking which values of x. We are looking for x values such that the derivative equals 0. So let's find the derivative first. So g prime of x. Again, I'm taking g of x and I'm going term by term. 3 times 2 is 6. X to the 3 minus 1 is 2. Negative 4 times 2 gives me a negative 8 on front. X to the 2 minus 1 is just 1. And then this guy is going to just be plus 2. Minus 1 goes away. All right, so my derivative is 6x squared minus 8x plus 2. Now we need to set it equal to 0. Let's go ahead and do it. So this is my step 1. My step 2 is I'm setting it equal to 0. I'm doing just what the problem tells me to do. So I have 6x squared minus 8x plus 2 equals 0. And I want to solve for x. Now, the first thing I notice is that this is a quadratic. And so I can, I can use the quadratic formula. But before I even do that, I notice that each of these terms can be simplified a little bit. Right? We can take out a 2. We can divide everybody by a 2. And what's left on the inside of the parentheses is 3x squared minus 4x plus 1. Okay. So now this is better because what I have is a prettier looking quadratic. I might be able to factor this, but you can just as easily use the quadratic formula, I think. So remember, our quadratic formula says that, if I have a quadratic of the form ax squared plus bx plus c, where a, b, and c are numbers, if I have that, then x is equal to negative b plus or minus root b squared minus 4ac, all divided by 2a. All right, so let's do it. Plugging in a, b, and c, we have 4 plus or minus the square root of 16 minus 4 times 3 times 1, all over 2 times 3. Simplify into the radical. This is just 4 over 6. Okay, square root of 4 is 2. So my two x's, 4 plus 2, we have 6 over 6, so x equals 1, and x is equal to 2, let's see, 4 minus 2 over 6 is a third. Okay, so what did we just find? We found the x values for which the derivative equals 0. Now remember, on a function, the derivative equals 0 at these flat parts, right? The derivative equals 0 at these flat parts. So let's check Desmos and see if we're correct. And remember, we're looking at the original function. Like the original function that they gave us, they're telling us that the derivative at the points on the function, 1 and 1/3, should be flat. All right, so let's check it out. So let me write this down. Let's see, 2x to the third minus 4x squared. So let's see, 2x to the third minus 4x squared plus 2x minus 1. All right, so we have this cubic looking guy, and we have a flat part right here at about a third in decimal form, right? And then we have another flat part right here at x equals 1. And so our graph is matching up with our computation, which is good. It's a good thing. Good thing to get the answer right. Okay, so these are the answers to this problem. Find the equation of the line tangent at the curve y equals 3x squared minus 2x plus 1 at the point 1, 2. What does this mean? Well, okay. We need to figure out the slope of the tangent line to a point. And here's the curve. This is the curve y equals 3x squared minus 2x plus 1. And what we're looking at is at the point 1, 2, which is right here. We want to know what the equation of this line is. And there's two things we need for the equation of the line. We need the slope, derivative, and we need the y-intercept of that line. Okay, and we can figure out this pretty easily. So the first thing is we need the slope. Now, Okay, so let's find the slope. And to find the slope, we find the derivative. So y prime is going to be, again, term by term using the power rule. This is going to be 6x minus 2 is our derivative. All right. Now, this is the function, right? I can plug in any x and find the slope, but there's a specific x I want to plug in to find the slope, and that's this x right here. This is y. So I want to find the slope at that x. So that's what I'm going to do. I'm going to plug in 1 into my x value right there. And so my slope is going to be 4, positive 4. And that kind of makes sense from the graph. It looks like it's about, has a slope of about positive 4. Yay, we have the slope. Let's figure out what the y-intercept is. Now, remember from back in the day, we have the slope-intercept form of a line, y equals mx plus b. And now we can plug in everything we need and solve for b. We know the x, y point. Y is going to be equal to when x equals 1, and the slope is 4. And now we just solve for b. So 2 minus 4 is going to give us b equals negative 2. And that kind of looks like it's about to cross negative 2 on the y-axis. All right, cool. So we got these two things. And so what is my answer? Well, my answer is just, what is my answer? Oh, the equation of the line. Okay, great. So the equation of the line is y equals 4x minus 2, just replacing m and b into, So that's the equation of this line right here. Now, if, you wanted to graph that line from scratch, we could certainly do it. Now, we know one of the points on the line is going to, also intersect this curve at 1, 2. So, let's see. So that's one of the points, and the y-intercept is negative 2. However, negative 2 is not really on the picture, but what we do have is a slope of 4, so we can rise over run from this base point. 4. Yeah, so we'll rise up 4, which is going to be right here. And then we're going to run 1, which is right here. Okay, so that point should be on our curve. And then we just connect the dots. And there's our tangent line. Beautiful. Okay. The distance of a rock blown upwards from dynamite is given by the equation S of t equals 160t minus 16t squared. First question, what is the velocity of the rock at 3 seconds? Okay, so remember, we are given a position function, distance, position, height. These are all synonymous words. So velocity is the derivative of position. So that's the first thing we need to do for part A. We need to find the velocity function. So v of t, let's call it that, velocity with t as our variable. Well, we're just taking the derivative of this position function. So derivative, again, part by part, is going to be 160 minus 32t to the first, or just t. So that's my velocity function from using the power rule. It says, what's the velocity of the rock at 3 seconds? Well, I need to plug in 3 in for time. So v of 3 is going to give me 160 minus 32 times 3. Let's pull out the handy-dandy calculator and see what's happening. 32 times 3, so 160 minus 96, and we got 64. Now, I don't have units here, but man, I wish I put units. How about we do this in, feet, where t is in seconds. Let's make those the units. Because if that's the case, then this is going to be 64 feet per second is my velocity. And it's positive velocity. That's one thing to note there. Now it says, what's the acceleration of the rock at 3 seconds? Well, remember, acceleration is the derivative of velocity. So we need to take the derivative of the velocity function for acceleration. So a of t, acceleration with time as the variable, or independent variable, is just going to be negative 32, right? The derivative of 160 is simply 0. The derivative of negative 32t is just negative 32. And so our units for this is going to be feet per second squared, okay? And if you don't know where that squared comes from, I encourage you to, think about it. Think about for a moment why the units of acceleration are what they are. All right, so here's my acceleration function. What is it at 3 seconds? Well, there's no variable. It's just negative 32. So that's my answer here. Right, because if I had a variable, I would plug 3 into it, but it appears that acceleration is going to be a constant number throughout this rock's flight, and that number is negative 32. All right. Oops. Let's go to the next one. At 3 seconds, is the rock speeding up or slowing down? Well, remember that speeding up, let's write it. Speeding up means one of the two things, right? We either have velocity is positive and acceleration is positive, or both are negative. Velocity is negative and acceleration is also negative. That was speeding up, and then the opposite is for slowing down. We have opposite signs. So at 3 seconds, velocity is positive, right? Because it's positive 64 feet per second when we plugged in 3. So that's true. But acceleration is negative because it's this constant negative 32. Okay? So this means it's slowing down because we have opposite signs of velocity and acceleration at 3 seconds. Okay. What is the maximum height the rock reaches? Okay. So first of all, notice that the position function is a quadratic. Okay, the highest power on the variable is 2. And so what this is going to look like, it's going to look like an upside down parabola with some maximum. And we can go in Desmos and plug this in, but how would we do this algebraically? Well, let's think about it. So when, basically what happens is the maximum height occurs when the velocity is 0, right? Because think about this rock being thrown upwards, okay? This is where the maximum height is. And the velocity is 0 because the slope of this line tangent to it is 0, right? That's the flat part of the graph. Another way to think about it is that this thing has to turn around. I mean, it has to stop eventually in order, for gravity to take hold and bring it back to the earth. So that's what we're looking for. We're looking for that vertex. And another way to see this is, where is velocity 0? Well, we have a velocity function. And all we have to do is set the function equal to a velocity of 0 and solve for t. Okay, so let's write our velocity function down. From above, velocity equals 160 minus 32t. And we're concerned with when velocity is 0. Okay, so we set this equal to 0 and solve for t. What time does this occur at? Well, let's see. Negative 160 equals negative 32t. So I believe this is 5. Let's check the calculator. 160 divided by 32. Yeah, we get 5 seconds. So at 5 seconds, So maybe I'll write a star. At 5 seconds, the rock reaches a max height of ... How do we find it? Well, we go to the height function, the original position function that we were given here, and we're plugging in 5 for t to figure out what that height is. So we have what was that function? 160t minus 16t squared. Let's check it out. Okay, so S of 5 is gonna be 160 times 5. We got 800 over here. Minus 400. That's just gonna be 400. So this is 400 feet. That's the max height here. So, if we were to, let's just think about it on the graph just for a second. So we have this, let's say this is 5 seconds right here, and then here's my maximum height of 400 feet. This is our time. This is our feet. And, maybe it looks something like this. And so let's think about what we just kind of gathered from algebra, not the graph. So the first thing we gathered was the following. We have the velocity of the rock at 3 seconds. It's 64 feet per second. Okay, so let's look at that on the graph. So this is 3 seconds. And so what this is telling me is the slope of this line is going to be what? Well, it's going to be 64, right? Because that's the velocity, okay? So that was the first thing we figured out. The second thing we saw was that the acceleration is constant throughout the rock's flight. It's always going to be negative 32 feet per second squared, okay? So acceleration is always negative. Then we saw that the rock is speeding up, the rock is slowing down at 3 seconds, which makes sense, right? Because the rock, as soon as we throw this thing up, gravity's trying to pull it down. So this thing is slowing down, right, at time equals 3. When is it speeding up? Well, it's speeding up when velocity and acceleration are both negative. So it should be speeding up on this time interval. So like at t equals 6 seconds, for example, that thing's going to be speeding up because it falls on this side of the parabola where velocity is negative and acceleration's always negative. So just keep that in mind. All right, guys, I hope this video was informative. I will see you guys for the next one. Have a great day. Hey guys, in this video we're going to be talking about Chapter 3, Section 2, the exponential function. And so we're going to use these two key facts. Both of these are proven in your textbook. I'm actually going to prove this guy right here, but you don't have to know how to prove it. Just, we're going to have to learn how to apply these rules. And so the first thing is that the derivative of e to the x is just e to the x. So the derivative of e to the x is the same as the function itself. And so if we were to take the derivative, so if we were to ask what is the derivative of y equals 2e to the x, what's the derivative of this? Well, y prime is just going to be 2e to the x. Okay, so the derivative is equal to the function, and the 2 doesn't really matter because of that very first theorem we looked at saying that, if you have a constant number in the front, it can stay there when you're taking the derivative. All right, so that's the first thing, and we're going to prove that in the next slide. The second thing that I'm not going to prove, but you do need to know, is that if a is a constant, being a number, then the derivative of a to the x is the same thing as ln of a times a to the x. Remember the logarithm function, ln is just, if we have ln of x, well, this is the same thing as log base e of x. Okay, so that's just, a fact from algebra. But anyway, we're going to be using these two things to answer some questions. And so the first thing we need to do is we need to prove that the derivative of e to the x is in fact e to the x. And again, you can skip through this video if you're not interested in this, but I think it's kind of an interesting proof, and it's a super useful idea in calculus that e to the x is equal to its derivative. And so what does that mean? Well, that means if we have e to the x, that its function value, so let's look at, say, for a function value of 8, well, that just means the slope of this tangent line is going to be 8. And same thing right here. The value of the function looks to be about 2, and so the slope of the tangent line is going to be 2, and so forth. Okay, so the key thing we need to know for this proof is that e is equal to the limit as n goes to 0 of 1 plus n raised to the 1 over n. And if you're curious about how this came to be, you should look at Taylor expansions, but this is just going to be a fact that we need to prove this. Okay, so let's start the proof. So we're trying to prove that the derivative of e to the x is e to the x, and so when we're trying to find the derivative, we use the limit function. So f of x plus h minus f of x all over h. And so in this case, we're trying to find the derivative of e to the x, and so we're just going to input the following here. We're going to say e to the x plus h minus e to the x all over h. And what I can do from here is I can rewrite this first term, e to the x plus h, using the product rule of exponents. And what that tells me is that I can sort of separate it like this. E to the x times e to the h is the same thing as e to the x plus h. All right, so I'm just replacing that here. Okay, so far so good. Now what I'm going to do is I am going to factor out an e to the x. So that on top, I'm just left with e to the h minus 1 all over h. And what I'm going to do next is I'm going to use one of my rules for limits to actually bring this e to the x in the front. So this is why can we do this? It's a property of limits. So as h goes to 0, e to the h minus 1 all over h. Okay, and so from here we're going to do some magic, because if we plug in 0 for h, we're still in an undesirable situation. And so I'm going to make a substitution here. I'm going to say the following. I'm going to say let n equal e to the h minus 1. Okay. And it follows from this, if I do the algebra, I get n plus 1 equals e to the h, right? If I just add 1 to both sides from this guy. Okay. And then remember that the ln of x and e to the x are inverse operations. And so what I can do is I can take the ln of both sides to sort of cancel out the e. Okay, so that cancels out, and I'm left with the following. I'm left with h is equal to ln of n plus 1. So I'm going to substitute this guy in for the numerator, and I'm going to sub in this guy for the denominator. So let's do it. Okay, let's see. We're going to do e to the x, limit h goes to 0 of n over ln of n plus 1. Okay. All right. Now, one thing to note here is the following. We have a relationship now since we made the substitution. We have h is equal to ln of n plus 1. Okay, we have this relationship between h and n. And so what that tells me is that as h goes to 0, as h gets closer and closer to 0, n is also getting closer and closer to 0, because the ln of 1 is just 0, right? And so the reason I'm saying that is because we can substitute h going to 0 with n going to 0 here. They mean the same thing because of this relationship we have with the equation. So there we go. Now we have the right variables, which is good. And what I'm going to do next is I'm going to multiply top and bottom of the denominator by 1 over n. Right? I'm allowed to do that. No one's going to stop me. So n times 1 over n. Right? Because essentially I'm just multiplying by 1 when I multiply top and bottom by 1 over n. All right, so here we go. Okay, I did that. So on top, what I end up getting is 1. On top, I get 1, right? N divided by n is just 1. And on the bottom, I'm going to use a property of logarithms that tells me that a times ln of b is the same thing as ln of b to the a. Okay, so using this property, I'm going to rewrite this as ln of n plus 1 to the 1 over n. Okay. Now, another property of limits tells me that, I can actually go inside of the ln argument and take the limit as n goes to 0. So this is another property of limits that says I can write this in the following way. I can write e to the x, and this property is going to be, if you're curious, it's going to be in chapter 1 of your textbook when we start talking about properties of limits. It's ln limit property. So we have e to the x, limit as, let's see, how should I write this? We're going to do 1 over ln limit as n goes to 0 of n plus 1 over 1 over n. And again, this is just by limit properties that I was allowed to do that. So the limit as n approaches 0 of n plus 1 to the 1 over n, well, that comes from this key fact right here. That equals e. This whole thing equals e. Okay? So what we end up having is we have e to the x times 1 over ln of e, right? Because all of this from our key fact equals e. And the ln of e is just 1, and so we end up getting e to the x times 1 which equals e to the x. Okay, and I'm going to put a little box there to say the proof is done. We have just proved that the derivative of e to the x is in fact e to the x. Okay, so that's the proof. Again, you don't need to know the proof, but it's, you know, it's interesting for some people to see where this fact came from. Okay, so now comes the easy part. We're just going to use those facts to evaluate these problems. So first one, again, is the derivative of e to the x is equal to e to the x. And the second one was the derivative of a to the x equals ln of a times a to the x. All right. So using, let's see, we have this guy is using the e to the x fact. So f prime of x is just going to be equal to 2e to the x. Remember, the derivative is itself. And here we need to use the power rule because this guy is not an x, it's a 2. So this is just going to be plus 2x. That's our derivative. Okay, moving on to the next one. 12e to the x, the derivative of that is just 12e to the x, plus the derivative of 11 to the x by this orange rule is just going to be ln of 11 times 11 to the x. So this is my whole derivative, g prime of x. Let's look at number 3. So y prime is going to be ln of 2 to the x by the orange rule, plus 2 times ln of 3 times 3 to the x. And again, this is by the orange rule. Okay, so that's our derivative, y prime. Let's do some more of these. So ln of 4, that's just a number, so we just treat it like, you know, it's a 2 or a 3 or anything in front of an e to the x. And so this is just going to be itself. So y prime is just going to be ln of 4 times e to the x. Okay, let's look at this one. So the first thing I'm going to do is I'm going to rewrite this before we take the derivative. Y is equal to 1/3. Right, I want to have that number in the front, 3 to the x. Instead of 3 to the x over 3, I can write it like that. And then the second part is going to be 33 times x to the negative 1/2. If I change this to x to the 1/2 and then bring it up to the numerator, it's going to be x to the negative 1/2. Now I can take the derivative. So y prime by the orange rule on the previous slide, excuse me, is going to be 1/3 ln of 3 to the x, and then we have plus. Now this guy, I'm just using the power rule because we don't have a variable in the exponent. So remember, I multiply these guys together and subtract 1 from the exponent. So this is going to be, let's see, well, let's just say it's negative 33 over 2, x to the negative 1/2 minus 2 over 2 is negative 3 over 2. So this is our derivative. All right, and the last one here, we have f of t equals ln of 3 to the t. Well, again, we think of ln of 3 just as a number, right? And so, you know, a number that your calculator can give you. And so we're using the orange rule right here for this one. So this is this, so if we take the derivative, f prime of t, that is just going to give us ln of 3, right? I have to take the ln of whatever this is that's acting like our a, and then I'm going to multiply by our original function, which was ln of 3 to the t. So this is our derivative. Alright guys, I hope this video was informative. Thanks for watching. I'll see you guys next time.